So by now we have seen already linear momentum and angular momentum. And remember that the idea of developing these concepts, in particular we saw it with linear momentum, was that we wanted to find another way of describing and analyzing motion. We had a Newtonian approach where we're going to have objects do the free body diagram, finding the net forces, and then using Newton's second law to say that the force is equal to mass times acceleration, which means that the net force is going to produce a net acceleration that then we can use with the kinematic equations to describe the motion for every time, right? And now we saw that with linear momentum we can make an approach where we first of all quantize how much of motion there is, and then we observe that a certain time later there is a difference in motion. And the only reason why there can be a difference in motion is if there is an external force acting on the system that is changing the motion, right? We remember that at the end you have the momentum is mass times velocity, and so if I'm changing the velocity, that means there is an acceleration, that means there is a force. So if I have a system with several objects, in the most easier case, take just a single one that has certain amount of motion, and we call the momentum the amount of motion. After a given time, if the velocity has changed, that means there is an acceleration. If there is an acceleration, there needs to be a force. But if the object is isolated, there's nothing to do a force on there, right? Forces always come in pairs, so it's action, reaction, Newton's third law. So that's what we said, if there isn't a change in the state of momentum, in the state of motion, that is because there is an impulse. An impulse, of course, being a force that's acting over an amount of time, right? The more time or the more force, the higher that impulse. And we saw the equivalent for the angular momentum, which was just that, the equivalent for angular momentum. When we develop angular momentum, in this case, just simply as the inertia instead of the mass, and the omega, which is angular velocity instead of velocity, because we're talking about rotational. And we came up with the same idea. Now we're going to say the conservation of angular momentum. If an object is moving a certain amount in rotational motion, it needs to have the same amount. And if there is a difference, necessarily it is because there is, in this case, we don't need to use vector, because there is a rotational impulse. And what's that rotational impulse? There needs to be a force acting over time. But now we just don't have a force, we have the equivalent of force in rotational motion, which of course is tau, which is the torque. So now we see, we have the analogy for linear momentum and angular momentum. Now as physicists were developing these ideas, they were thinking also what other quantities, these quantities are conserved, right? That's what we see, and that's why they're interesting, because now we cannot do, as we have seen in the problems, a bookkeeping approach to the problem of motion. Like if we quantize how much motion there's at the beginning, we can figure out how much, there needs to be the same motion at the end unless there's an external impulse. And once we know that, for a particular item, if we figure out all the other items, we can completely determine its state of motion. So in a way, this is an accounting approach to doing physics that doesn't rely on actually solving the different equations of motion for each one of the objects, that we can instead we can just take the sum of all the objects, understand that they might interact with each other, but whatever was at the beginning needs to be at the end. And at the bottom of everything, of course, is the principle, which is more philosophical, which is the ex nihilo nihil fit. Out of nothing, nothing comes. We cannot take an object, close it in a box, say that that box is really isolated from the outside, and open the box and see that the object is moving, because that motion will be coming out of nowhere. And if we accept a single instance when motion is coming out of nowhere, then we have no legitimacy anymore to say that you cannot use that mechanism of out of nothing coming something in any other instance, right? Accepting or one single violation of that principle means that we are just giving up on the possibility of analyzing the world, because we're giving up on the world being a rational construct that can be understood. And as we saw in the first chapter of introduction, this is one of the premises for the possibility of science. It's a metaphysical and epistemological premises. There is an order in nature, and the order can be known. If we say things coming out of nowhere, then we cannot just talk about that anymore. So this is from the point of view of angular momentum and linear momentum. This is from the point of view of calculating the amount of motion. But these are just definitions. So it happens, it's a mathematical definition of the amount of motion, if you wish, right? Either translational or rotational. And we come up with a mathematical description. Why? Because at the end of the day, science, in particular physics, is the quantitative study of the study of the quantitative aspects of objects in motion. So we're trying to do quantitative assessments of things that we are studying, right? We observe in the world certain phenomena, and then we try to mathematize those phenomena, and as we do in physics. And so this is just an example of that. We just came up with this idea of there is an amount of motion. Well, yeah, intuitively we understand, but we need to offer a mathematical explanation, and this is what we give. But the question is this the only mathematical explanation? And the answer is not. And you can come up with whatever approach you want, but it so happens that this one, it is conserved, and why is what's so powerful. But still, there's another one, another approach to this problem of analyzing motion from the bookkeeping approach, if you wish, which is by following the root not of Descartes and his linear momentum, and the equivalent for the angular one from a route that Gottfried Leibniz, the German physicist, studied, and that's the idea of the viva, which is applying the force. What is the force coming? And is the concept of energy. For Leibniz, he realized this is not a complete definition. We can use a definition instead of being proportional to the mass and velocity was proportional to the mass and the square of the velocity. We will see how that actually accounts for, or is that the fundamental of the kinetic energy later, but for the time being, we see that there is, or we can accept that there is a third approach, and that approach is just by using what we call energy. Now, of course, energy, it's easily the most elusive concept in physics. It has extraordinary ramifications in the discussion of philosophical discussions of exactly what is energy, but energy is the most fundamental entity that physics deals with. And in fact, in modern physics, you will see that you don't deal with energy anymore, you don't deal with forces anymore. We actually deal with energy and conservation laws, right? Physics 2053, that's a way, but that's what we discuss in the lectures when we say there's two main ways of answering what is energy. There's the first approach that we could say is kind of Newtonian, and from the Newtonian perspective, we could say that this is the vectorial mechanics, if you wish, and that's of course that the energy is the capacity of doing work, right? Now, of course, the question becomes then, what is work? What is that? And that's what we'll introduce next, right? But there's a second approach to the concept of energy, which is that the analytical mechanics one, or from which analytical mechanics is developed, which is just saying it's a bookkeeping approach. And what do we mean by that? So what do we mean by that? Well, it's exactly the same thing we just did with momentum. It's just taking a different mathematical formula. So don't think of what is exactly energy. We'll come to the nature of energy towards the end of the chapter. From the point of view of the problems, it's relevant. What's relevant to know is that we can use this as just a mathematical tool. If you remember when we were discussing the introduction of Copernican model and saying instead of having a geocentric model, we're going to have a heliocentric model. At first, it was introduced just to say it's a mathematical tool. So in physics, and in fact in modern physics, we're walking away from analogies of the real world and going more into the abstract and exotic, and then we're relying less and less on intuitive ideas of models of things that we see around, and we're getting more into a mathematical approach where everything is described in terms of mathematical models. It might be more abstract, and then you're required to train your intuition, but it still is much more powerful. In fact, all modern physics and quantum physics and quantum field theory, etc., are going to be based on this approach of energy as being a bookkeeping quantity that we need to track. And we're not going to be tracking forces acting on objects, because remember, for forces here we need to have the free body diagram and analyze all the forces. And this is okay for one particle, maybe two, but if you had a million of those, that would be absolutely impossible. With the energy, with the bookkeeping approach, we solve those problems. So we're going to see kind of the ideas of those two. We will start by introducing what is work from the point of view of physics. And again, it's very important that even in physics we use words that you use in your day-to-day life. You do not confuse what do we mean in physics. In physics we mean something very precisely, because that's why we use mathematics, to be rigorous and precise on our calculations, and work is going to be force times the displacement that we'll see now. But also we're going to be able to make an understanding that the energy is just a mathematical number, whatever that is. We're not concerned of what is its nature, because that's actually a question of metaphysics, not of physics. But what we're more interested in seeing that thing, that number that we came up with, is actually pretty functional, it's pretty good to be able to solve very complex problems that otherwise from the Newtonian approach wouldn't be solved, or solvable, right? So again, this is this idea. If you wish to understand work, the first intuition that you can have is just the intuition of capacity of doing work, and we will make sense of this. The other one is the analytical approach, which is the booking approach. And what's the reason for that is that if you analyze, for instance, a particular example that you can make is, let's say that you have a spring and then you compress it and you put a ball in here, right? And so of course you know that the moment that you release the spring, the ball is going to start in motion. But if I ask you what is the linear momentum in here, the linear momentum is going to be 0. So there seems to be somehow a missing part of describing the motion, and at the end of the day everything that we want to know is describe motion, right? We want to describe motion, and so we're saying, oh, I can do Newton's laws, or I can do conservation of momentum, and I'm going to do now conservation of energy. And this idea of energy shows why sometimes momentum might be a little bit more limited. Also in actually determining momentum in the case of Newton's cradles, as we will see in the lecture. You don't know exactly how many balls are going to come, because if you go twice the velocity, you could have 2 balls with the same velocity, or just a single ball with twice the velocity, right? That needs something else to be fully described. So in the case of the spring, we see that even though there is no motion, there's something internal to that says there is motion in here. There's some sort of potential for motion, something that is not still actual, if we use the Aristotelian terminology, right? It's potential, I mean, it's not actualized, but can be actualized. It means that this is going to become motion. So energy at the end is profoundly linked to the idea of motion. It's just a way of describing motion. And now we will see it's going to take different forms, because we're going to distinguish when we have energy, because motion is actually happening right now, which we call kinetic energy, and we're going to have energy also when it's positional energy, as we discussed, that is going to be based on typically a field, but basically a force that depends on position, right? So those are the 2 energies that we're going to find, kinetic and potential, but there's still many more energies, right? There's capacity of getting in motion, something intrinsic and related to motion. Let's see then first the definition of work, and then we will understand and see the definition of the other forms of energy that we consider in Physics 2053. So in physics, we're going to describe energy as the capacity, or a way of describing energy is the capacity of doing work. And the question, of course, is what is work? Well, work in physics is defined as the product of the force times the displacement. And it's very important that we observe that both the displacement and the force are, in general, vectors. And so if we remember the description that we did in vector analysis, when we have the scalar product or the dot product of the 2 vectors, that's equal to the product of the modulus of the 2 vectors times the cosine of the angle between them. So if I have a force acting in this direction, let's say, and then I have a force acting, and a displacement that is produced in this direction, this would be the vector. Even if I'm not going to, on purpose, I'm not going to align them with the axis, that's irrelevant, and you'll see why in a second. Then this angle over here is going to be theta, right? And so we can see that if I rearrange this, I can actually just rearrange it as delta x, force times cosine of theta. And then I ask you, do you recognize that? Well, that is actually, let's take that triangle here. So we have the force, and then we have the theta, right? This is the delta x. And I'm just going to rotate them so we see them clearly, right? So I can have now delta x here, and then force over here. And I ask you, what is the modulus of f times the cosine of theta? Well, the modulus of f times cosine of theta, the cosine of theta is going to be so katoa, the adjacent. So it needs to be something that's happening here. How much? Well, actually, it's just all the way only up to here. This is f cosine of theta. And what is that? That's the x component of the force. Or rather, is the component of the force in the delta x direction. Because again, delta x here is not a line, but the force is going to be just simply this one. Right? So then we see why we discussed in vector video that actually delta x, that a scalar product is actually the product of the magnitude of one vector times the projection of the other vector onto the direction of the first one. In this case, it's going to be the modulus of the vector of the force of, it's not the modulus anymore, of the force into the delta x direction. And this is important. Why? Because if I am applying a force, if a box is moving in this direction, purely horizontally, and I'm applying a force at a 90-degree angle, then theta is 90. How much is the work that I'm doing on that object? That's going to be f times delta x, which is going to be the x component, which is f cosine of theta. What's cosine of theta? 90. So what's that? That's going to be 0. So we're going to find that this is 0. So the force needs to be aligned. In the case where theta is equal to 0 degrees, then we're going to have the work is equal to f delta x, of course, and then cosine of 0, which is this is 1. So that's just simply f delta x. And if you have, let's say, cosine of 60, let's say that the angle are 60 degrees, right? We could do 45, it doesn't matter. Then we're going to see that the work, which is W, right? That's the W, clearly work. It's going to be the force, delta x, and then delta x, and then cosine of 60. In this case, 60 is 1/2, so that's going to be 1/2 of the force modulus, displacement modulus. What is telling us this? What is this thing telling us? You see, as you increase the angle from being completely aligned, as you increase that angle all the way up to 90, what's happening with your work is being reduced. Why is being reduced? Because you have less and less of the force in the direction of the displacement, and so you are not contributing to the motion in that direction. Therefore, you're not really doing work because you're not changing anything about the motion. And again, the idea here is to describe motion. And so if I'm applying a force, that's all good and dandy, but the force needs to be aligned with the direction of motion to actually claim that it has certain responsibility of that. That's why it's a scalar product, because I'm trying to find how much of my force is actually aligned in the direction of the displacement. Of course, if the displacement is 0, holding an object up, it doesn't do any work on the object. And another thing which is important, excuse me, on here is to remember we're trying to make a definition of a theory that allows us to describe motion. And always when we describe motion of an object. So when we're saying work, we mean work on that object. And so when I say I'm holding the dumbbells on the gym and I'm just getting tired, I'm getting tired, but I'm not doing any work on the dumbbells because the dumbbells are not changing their state of motion anyways, right? So then there's no displacement, there's no displacement, there's no net force on that. But anyway, I'm not changing my displacement, then I cannot have a work. If I'm pushing on a wall, the wall is not moving. Delta x is 0. So am I doing any work on the wall? No, I'm not. I'm getting tired, yes. But also I'm getting tired, as we will see later towards the end of this, when we see all the forms of energy. Because my muscles to be working, they need to be consuming all the time ATPs and all these biological ways of being alive. Basically, I need to be alive, right? Because if I took like a bookshelf and I put my dumbbells up there, obviously I understand there's no need for energy. That thing it is the way it is. But when I'm doing it myself, I need energy because I need, at the very least, energy to keep myself alive. And then, of course, if you get much more technical, you're going to see that whether the muscles are in a relaxed state or if they're actually stressed or compressed, and then they need to be all the time generating the biochemicals that keep them in that compressed or stressed state. They're not relaxed, and therefore they need to have an extra of energy to produce that, and that's biochemical energy. It's another form of energy, but we do not account for that sort of energy in our description of physics 2053. We're only going to be accounting for two types of energy. Well, let's discuss them now, which are kinetic energy and potential energy. Let's see what they mean now, but just very important, remember the energy is the capacity of doing work, and work is applying a force over a displacement. If there is no displacement, there's no work. If there's no force, there's no work. And if there's no component of the force in the direction of the displacement, there is no work. Do not get confused yourself doing a force, which you are an animated object, right? You're alive. You do not confuse, you should not, or you obviously will get it wrong, but don't confuse work in a general sense with work done on the system. Work is going to be related to the motion, and motion is related to energy. Energy is the capacity of doing work. How do we see that? If I pull up some dumbbells and I'll hold them there, whether I wait 1 day, 20, 50, or 1,000,000 years, the amount of work, the capacity of that dumbbells to do work, which is to transmit somehow or start a motion or change a motion, is going to be the same. I'm not changing it, so therefore I'm not making any balance. I don't have any exchange of that energy, which is a way to say I don't have a change in the capacity of doing work, which is putting an object into motion, right? Remember, energy is a way of doing bookkeeping to track motion. If the motion happens the same whether I'm 1 day or 1,000,000 years, means that there is no really exchange. So from the point of view of bookkeeping, there should not be any work because there's no exchange in energy. And so work, we can understand it actually as energy in transfer. And that becomes much more clear after we study the principle of conservation of energy. Let's see the types of energies, and let's see also the conservation principle. So say that you want to buy something, right? Whatever that is, a house or any other thing that you want to buy. If you can afford it or not is of course related to how much money you have. But as millionaires in particular, millionaires know very well, not all money is the cash that you have in your wallet, how much physical money you have. You might have money that it's, for instance, in the form of a digital annotation in a bank balance, right? If you go to your Chase or Wells Fargo or whatever bank you have, there's a number in there, right? And that number is not cash, but it's still money. It's something that you can convert into the exchange of goods and services, right? And what about, for instance, if you have stocks, or what about you have a Bitcoin or any other of these cryptocurrencies, or what if you have you have lent some money to someone, right? So there, or you have other assets, you have maybe a house on the beach or something like that. You could always use those assets and all those components to acquire the item that you want. So in a way, you say that money in general is just the purchasing power, is the power to actually exchange a good. Now, from the point of view of energy, we can make an analogy with that. Energy is going to be like money. Energy is our currency in different situations to exchange. We exchange in the form of work to actually gain the capacity of doing work, which is actually going to be related to motion at the end of the day, right? And so the same way that we're going to say you have physical assets and you have cash and you have this and you have that, we're going to say, okay, you also have different sorts of energy. So what sorts of energy are we going to have? We're going to discuss only two types of energy. Each one of those energies is going to be describing a different physical aspect. So the ones that we're describing is certain, in physics 2053 are going to be only kinetic, which is says is motion, and the other one is going to be potential. But there are other forms. For instance, if I wanted to say what is the form of energy related to a nuclear reaction, it's going to be nuclear energy. Or what is the form of energy that I can have from a battery? It's going to be maybe electrochemical energy. Or as we were discussing in the muscles when I'm doing some exercise, well, that's biochemical. There are many different ways or many different forms of energy, each one associated with a different type of physical phenomena or a different physical aspect. You will see in physics too that you have also electrostatic energy, and you're going to have then energy that comes from electromagnetic field. So those things are other forms of energy. The ones that we are studying are only simply kinetic and potential. Each one of those we are in particular studying two examples to keep it simple. Things are moving, and things move in two ways. One, they move in translation, and they also move in rotation. Therefore, we can introduce a definition for translational energy, which is 1/2, which is going to be called K sub E sub T, and that's 1/2 of mass V squared. You remember when said Leibniz at the beginning thought about an expression, he was hinting about this. This is what we call Ka, is kinetic energy sub T. This is not K times E. We're just using this notation with two letters because we're actually running out of letters. So we could use capital E, but in the future you're going to introduce electric field, and then electric field is going to be E. And so what do you use for electric field then if you're already using E for energy? It gets messy. So in prevention of that happening, let's keep it key E, which reminds you is kinetic energy, and sub T because it's of the translation type. Why is translation? Because it has mass, which is kind of inertia, and it has velocity, which is that velocity of the object. Now, it's not going to be surprising that we also have rotational motion. And so in rotational motion, we're going to have kinetic energy because it's already actual, and we're going to be sub R, which is rotational, and it's going to be also 1/2. But how much is the inertia in rotational motion? By now, of course, you know is the moment of inertia. And how much is the velocity we're considering in rotational motion? Is omega squared. So now we're going to see the angular equivalent of inertia, the angular equivalent of velocity. Angular velocity, moment of inertia. And that's the formula for rotational motion. What objects have kinetic energy in rotational form? Whenever you have, for instance, a spinning top. That top is spinning, and because it's spinning, has a kinetic energy. If I throw a ball or a billiard ball or a train going on a track, that's sort of translational kinetic energy. It goes in a line, and it's proportional to the mass of the object and times the velocity. These two objects are energies of the motion. They're already actual, if you wish, right? They're already actual because the object is already moving. And so we're going to have also potential. And if you remember, Aristotle was distinguishing between potential and actual properties. And we said, well, you know, a block of wood or clay, it's potentially a sculpture, but it can be also potentially like a jar or a plate or whatever it can be, right? You can think of different things. So that is things that the object is potentially, but needs to be actualized. Well, this is going to be something similar. There is something potential, there is something related to the object itself, which is the result of its position when experiencing a force or under a force. We could say a force field, but that's too confusing at this stage, so let's just keep it as potential. And what sort of forces we saw that depend on position? We saw, well, actually we only saw one explicitly, which was the elastic force, right? Remember that the elastic force or Hooke's law, we said it was minus K delta X, right? So obviously the farther away you are, the more the force is. So we're going to see that the farther away you are, the more elastic potential energy you're going to have. Why is it potential? Because it's stored in the system, right? So it's stored. This one is kind of stored. It's internal to the system and needs to be actualized. At some point it can be triggered and it can be actualized. In the case of elastic energy, we're going to find that this is PE. Again, it's not P times E. This is potential energy, and we're going to call it sub E, elastic. And that's 1/2 of K, and this is going to be delta X squared. Now, we're not deriving these equations. We are just giving them. We are enunciating them. Why? Because you do not really, we do not derive energies, right? We define these formulas based on the observation, but we cannot observe energy. You observe the mass, or you can observe even like the volume and measure them. We cannot access energy. Energy is an abstract entity. We do only observe the effects of energy, right? So just take this for granted. There's nothing here to do. You just said we found out that this equation is useful, then we use it. That's all we're saying in here, right? It's a mathematical approach to characterize that idea that there's something here, there's a stored energy. Again, energy is the capacity of doing work, and work is related to applying a force over a distance, means changing the state of motion of something else. So I need currency, I need my purchasing power, I need my power of changing motion, and sometimes the power is in the bank, it's not in cash. This, let's say it's cash, it's ready to be used. This one needs to be somehow actualized, right? It needs to extract from the ATM or using any other mechanism, to give the analogy. So that's the idea of potential energy. Energy is stored. And the other form that we're going to see in potential energy is probably the most trivial one that you already know, which is of course the one for the famous apple of Newton. If you have an apple in the tree, nobody touches it, there's no force, but suddenly, pump, it just falls. I mean, of course, there's a force, which is gravitational force, otherwise it wouldn't fall. But I'm saying that nobody touches, suddenly just we see it fall. And what's that? What's that? Gravitational energy. So it had no motion, right? Gravitational potential and elastic potential. It had no motion and suddenly has motion. So from our perspective, which again, we're using energy to describe, these are all forms of energy. So we're using energy as a bookkeeping approach, as a mathematical approach of calculating and describing motion. Then I see that things moving already have energy, whether they're moving in translation or rotational, but they're also going to have moving depending on their position. Even if they're not moving right now, there is something intrinsic to that. We said that with the example of the spring being compressed that Leibniz was probably considering. There's something in there already stored that somehow is related to motion. It's not expressed right here, right now. And if we describe the momentum of this, it would be zero, right? So how do we call that? That's particularly the potential energy. And in the case of gravitational energy, we're going to call PE, again, not P times E, but PE, a single entity, and sub G for gravitational, and that's the very famous mg and the delta y. What is delta y? That's the height of the object from the surface that we always take as zero. We need to define a 0 point. In our case, we're always going to define 0 for gravitational as the ground, and 0 for this is going to be the rest position of a spring. The idea with potential energy is because it depends on the position, actually you can shift the reference point. But again, this is very, let's say, very technical for the level of physics 2053, so we don't really need to pay attention to that. Let's just say the change in height is going to produce a potential energy. If I have an object here, or I have the object here, what is different in terms of the position of the object? What's the different in the position of the object? That it has stored a different amount of energy, and that energy is the capacity for that object to do work. And now we can go back to the example where we were saying, oh, let's say that you're holding the dumbbells here, and then you're holding them stationary, and then you're getting tired yourself, right? Well, you're getting tired because anyways, even though you are not doing, and we say, what's the work, right? Work is force times displacement, but there's no displacement here, it's stationary, so there's 0 work. Work on the dumbbells, okay? On the dumbbells, work on the dumbbells. Why are we saying there's no work on the dumbbell? Because we're not changing the energy stored on the dumbbells. The energy of these dumbbells is purely given by the height they have with respect to the ground. If I lift them, I'm giving energy them, so therefore I need to do work. That's why I'm lifting them, right? I'm giving them work. I'm putting work, which is a way I'm transferring the energy. I'm making that exchange of my currency, which is energy, into the system. So through work, we exchange energy. Work is just the key word of exchanging energy. So this transaction is me pulling from the object. I'm putting work, I'm doing work on the dumbbells, which means the dumbbells are going to have 0 energy on the ground, and suddenly they start to store energy because of their position. How much energy is stored, of course, is going to depend on the final position. So when I'm lifting them up a little bit more, I'm increasing the position. I need to put work because I'm putting energy. But when they're just hold them in there, and I hold them for 1,000,000 years, we're not changing the height. Therefore, there's nothing is changing internal to the dumbbells in terms of the capacity of doing the work, means the capacity of getting into motion or making something else move, because it has the same, it's just given by the potential energy. So that now makes more sense. Even though at first was a little bit obscure, we start to see the connections of work is just the exchange of energy, and energy is telling us the capacity of doing work. So it's still a little bit circular, but the important thing here is that we're seeing is a bookkeeping approach to this. Whatever this is, eventually it's again a matter of metaphysics, but up to a point, but actually the fundamental, but we still can say a few things here, right? So again, we're going to have potential energy, which is usually depending on the position, basically because there's a force, either elastic force or weight, and that's sort of stored in the object. And then we're going to have the actual one, which is not potential, it's actual, which is the kinetic one, which is the one associated with motion. And because there's two types of motion, we're going to have kinetic, and we're going to have kinetic translational and kinetic rotational. Typically in textbooks, by the way, you will never see this is called kinetic translational kinetic energy. That's because mostly you just describe it as kinetic energy and this as rotational energy. But the truth is that the kinetic translational energy, the translational kinetic energy is the one related to translation, and you can make the one for rotational. And to keep this analogy always in there, so we describe translational and we describe rotational, we're going to try to force ourselves to always say kinetic energy translational. But in textbooks, typically without the T, kinetic energy is given by this formula. Just be aware what they mean, it's important, the notation is free, but just understand what is the physical concept that you are describing in here. An object moving within a circle, right? It's moving rotational. We're going to be able to also describe that it has a kinetic translational and a rotational, depending on how we want to describe that. But an object moving on a line, it doesn't really have a rotational energy if it's not rotating. And that's also going to be back, as we will see in the problems, related to the problem of Galileo. Galileo had the inclined plane, and then he said, okay, up here you have, now we're going to be able to analyze it, right? Now up here you have potential energy because of the position. As you go down, that potential energy is going to go to zero, and the kinetic one is going to increase. Now, in reality, you not only have translational motion, this ball is rotating, and if the ball is rotating, you're going to have this and you're going to have this, right? So that's also something to bear in mind. So all these forms of energy, there's many more forms of energy that we're not introducing. All the ones that we're studying in physics 2053 are going to be translational and rotational. From the point of view of kinetic, those are motion already happening, and potential, which depends on the position, so to speak, is the energy stored. Those are going to be gravitational and potential energy. PE for potential, KE for kinetic, both are forms of energy, both are the same. The last thing that we need to say is the conservation principle of energy. So far we've been taking for granted. We were saying that work is the transfer of energy, and energy is just the capacity of doing work. But we haven't demonstrated that there is indeed a link between the two magnitudes. That's answered by the work-energy theorem. In first energy theorem, first of all, this theorem was developed for kinetic energy, and this is the only one we're going to see because we actually don't have the math to go beyond that. But this is a theorem that works for any energy, any type of energy. So we will generalize it. We will show it first for kinetic energy, that there is indeed a link between work and energy. It is not granted. And once we establish that link, and we establish it mathematically, because again, remember, it needs to be always quantitative. All our description of the natural world is always quantitative. That's what allows us to do prediction. If we do that analysis, if we actually came up with definitions, arbitrary if you wish, that we presented before for kinetic energy and potential energy, and we came up with the definition of work, which again is arbitrary, then we're going to be linking energy and work, and we're going to show that they are indeed linked. But once we achieve that, then we have the mathematical framework to be able to do this bookkeeping approach to solving problems, as we will see at the end. We will again do it for kinetic energy, but this can be generalized for any sort of energy. So let's start by saying that there is an object that we observe. There is an object that has certain velocity at first. At t sub 0 has velocity v sub 0, and an object, the same object at later time, it has a velocity v at time t, right? We can even take t sub 0 to be 0, which doesn't irrelevant, but doesn't matter. Let's keep it just there for the time being. And then we say, okay, this object is changing its velocity. Therefore, there is a change in velocity. If there is a change in velocity, there is an acceleration. If there is an acceleration, there is a force. Right? We know that. That much we know. And then we remember, okay, but what's the definition of force? Of work. Well, the definition of work is a force applied times the displacement, right? Where the displacement will be from here to here. We're kind of saying, what is the force responsible for this? Well, the force is acting from here to achieve that, and that's acting on the displacement, and is the force given F. But what's the definition of work? Of force? Force is mass times acceleration. So let's write, force times mass acceleration. So we're going to have this, right? So far so good. So do we recognize this over here? What is A times delta x? So let's write ma delta x. Do you recognize this? Let me go back to the kinematic equations. Let's say that you were trying to solve this problem, and then you will start writing, well, do I know the initial position? Do I know the final position? Do I know the initial velocity? Do I know the final velocity? Do I know the acceleration? And do I know the time? And there was a scenario where now we're going to know v sub 0, and we also know v, and then we also know the displacement, or kind of the displacement is over here. We don't know it. We don't know the acceleration, but we certainly do know, and we don't have any information on the time. So what happens when you have no information on the time? Well, when you have no information on the time, you just use this equation. And then you're saying, aha, so here it is. So what if I solve for A delta x? So I see that A delta x is actually this. Good? So A delta x, from my kinematic equations, I know it's equal to that. So let's write that here. That's equal to mass, and then the parentheses. Let's do square parentheses. That's going to be 1/2, and then v square minus v square sub 0. And I close this. Okay, let's just expand this. How much is that? That's going to be 1/2 mass v square minus 1/2 mass v square sub 0. And a second aha moment. What is this? Well, that's the kinetic energy, the translational one. And what is this? That's the kinetic energy, translational, at the beginning. So what do I have? I have kinetic energy, translational at the minus kinetic energy, translational at the beginning. And what is the difference of these two things? What do we use in physics or in math when we want to describe that we're making the difference? We're calculating what is different, what has changed. Well, the change is described by, again, delta. And so what I found here is that work, it's equal to the change in translational kinetic energy. This is the work energy theorem, and it's extremely important because this shows indeed the connection there is between energy, of in this case only kinetic energy, but we're going to generalize it, and work. Every time we have a change in energy, the energy needs to be coming from somewhere. How do you make that transfer? You make it with work. There it is. Work is going to be to energy what impulse was to linear and angular momentum. So again, every time I have an energy change, it is because something is producing that energy change. At the end of the day, energy is just describing somehow motion. And so if I have that change of the total amount of motion, where now I'm just saying amount of motion is linear momentum or angular momentum, now I'm saying energy is another way of describing that motion. Well, that energy is changing means that something external is acting. What's that external thing? That's the work. So again, very important when we do principle of conservation, we're going to say that work is the responsible for the change in energy. Let's write it in here. So we're going to be saying that instead of kinetic energy, we're going to go to any sort of energy that we just can call, if you want, E, or we could call E total. I don't know, how should we call this? But anyway, E total, let's say. The total energy is going to be what? The sum of the kinetical energy in translation, but you might also have kinetic energy in rotation, and you might also have potential energy in gravitational, and you might also have potential energy elastic. And in fact, you can have many other types of energies that we're not describing, right? We could have here chemical, or we could have here biochemical, or we could have here nuclear, or we could have here electromagnetic, or we could have here whatever, right? Any type of energy that we have is going to come in here. What we are saying with the theorem is that the work is actually the difference in energy of the system. Every time that we have a system, we can calculate the initial energy, we can calculate the final energy. If there is any difference, it is necessarily because energy is leaving the system. That money is leaving or money is coming in, right? That's the sign of work. When work is positive, energy is increasing. When work is negative, energy is decreasing. We see it over here. we see it over here, right? So that's the difference that we're talking about. The increment is going to be negative when it's decreasing, the increment is going to be positive when it's increasing. What's responsible for a change of energy? Work. Now take the entire universe. The entire universe contains everything that exists. So there's nothing outside. So is anything from the outside being applying a force inside the universe? No. So what's the work in the universe? Zero. So what happens in the universe? The universe conserves energy from the beginning of time to the end of time. It cannot be otherwise by definition. So what usually happens in modern physics is whenever they see that one of the principles of conservation it's kind of violated, it is broken, I try to figure out, oh, maybe we're not considering something, and a new aspect of nature is described, right? And that's a very important approach, but we're not giving up the principle of conservation of energy because it's foundational. So it's very important. Now, this connection being made, changes in energy, our work is the expression that justifies that we have been saying all along, work is transfer of energy, right? We could have introduced energy simply saying, oh, energy is a bookkeeping a quantity, and I'm going to describe one that when the object is moving translational, kinetic translation energy. I'm going to describe one when the object is rotating, rotational kinetic energy. I'm going to describe one when the object is up there because I feel that somehow it's storing energy, so I'm going to call that gravitational, and I'm going to see that it stores one when it's in spring and it's compressed or it's stretched because it's going to get in motion very soon, so it's kind of storing energy, it's kind of storing that thing which is the amount of motion, that again is what I'm interested in. I'm always interested in describing motion. I'm finding alternative ways of doing so that do not require making balance of forces with Newton. Well, here we have it, energy. And now I'm going to say, why can I change energy? I can only change energy whenever there is work. Work in the system is going to be increasing energy. Work out of the system is going to be decreasing energy. There is one aspect which is more interesting from the point of view of engineering than actually fundamental physics, but anyway, which is the idea of power. Power is, we want to know, let's say that you have to raise an object from the ground. Let's make a very simple example. Okay, let's make that this is the building, and you want to take the object from here all the way to here. And this is 0, and this is y. So you say, what is the change in energy in here? Well, we can say, obviously there's a change in potential energy because of the position. When position change, always things, oh, is there any potential energy changing? And in fact, there is one which is kinetic, which is potential gravitational. So what we're going to see is that indeed we're going to be making a change in energy. So potential energy at the beginning, gravitational at the beginning is going to be 0. At the end is going to be mgy, right? And so the difference in potential energy is going to be just mgy. So this is non-zero, which means, remember, that the change in energy is the result of work. So now I'm asking, how do I do that? Well, I do that because someone is doing work. Maybe someone is pulling it up like this, or maybe someone came here and came through the stairs and went like this. At the end, what matters is the change in position. And so both are increasing the same amount of energy. Why? Because the final state has the same stored amount of energy. It doesn't matter if you go to China and come back, and then you go with the ball. It's ridiculous. It's what? It's very inefficient, we say, right? So this is also the idea of how much of the work that you're actually doing goes to the system that you want to put the work on, right? Which is the why combustion engines are inefficient, because, for instance, there's heat energy, energy living in the form of heat, as we will see in thermodynamics, and so not all the energy of the combustion gets converted into motion of the car, which is your goal, to move yourself and propulse yourself, but some of it is being wasted, is being lost in heat and this and that and noise, and okay, that energy is kind of equivalent to this. We're not putting all that. So that will allow us to introduce the efficiency, which is how much of the work goes exactly to where you want to go, and we will see that in thermodynamics. But for the time being, let's just focus on this. This is independent, the amount of work is the same. But let's say that one takes, this one takes 1 second or 10 seconds, 1 second, and let's say that this takes 10 seconds. And then you say, how do I distinguish these two things? This is distinguished through power. Power, capital P, is defined as work over time, or if you wish, how much is the change of energy in the time. And this is going to be relevant because, of course, this is going to be much less powerful than this one. So sometimes when you are interested in how fast the transfer of energy happens, this is the equivalent of the velocity. Remember, velocity is how fast you change position. Now we're saying how fast you change energy. That is what we call power. And it's another metric that we can introduce to describe motion. Why? Because in certain systems are exchanging energy faster than in others, and sometimes you're going to be interested in changing fast, sometimes you're going to be interested in actually in the opposite. So that's why we introduce power as a metric, the same way that we introduce velocity as the change in position, the rate of change in position in time. We're going to introduce power as the rate of change of energy in time. And that's the last thing that we need. We can go now and solve some problems. Let's see some problems on applications of these concepts of energy, work, and power. So question number 1 in the discussions says that there is an incline with a block, and there are 3 forces. Incline is 30 degrees, and there are 3 forces acting in this. There's F1, there's F2, and there is F3, right? Remember, vectors don't have a position, so you could draw it the same way just by making the diagram and just take the center of the object. If this was the free body diagram, you would do F3, F2, and F3. So that's equivalent to what we just draw in here, right? Okay. In this case, actually, it's not that important anyways. We're going to have to calculate what's the work that each force does. So how do we calculate that? We have that F1 is 40 newtons, F2 is 20 newtons, and F3 30 newtons. And the problem also says that it moves 80 centimeters up the incline. So we can say that the displacement is 80 centimeters, which of course is 0.8 meters. Okay, so what is the definition of work that we're going to be using? Well, work is a force times the displacement. But if we use vector notation, then we have to remember that this is the modulus of work, modulus of displacement, and the angle that they both make. Or we can rewrite this as saying this is the displacement times the component of the force in the direction of the displacement. This is what we mean by that. It's F sub delta x, because this is in the direction of the displacement. If the force is completely aligned, that's going to be the force itself, but if it has an angle, as some of these, we're going to have to decompose into what? Into the direction of the displacement and the direction of perpendicular to that. So what is the direction of the displacement? Because the box is moving in this one, it is convenient then to use this set of coordinates, where we select this coordinate, let's say, as horizontal, and then this one as vertical, right? We can call them x and y, or x prime and y prime, whichever way you prefer. And then the object is going to be moving in x direction, right? That's the horizontal. So each one of the forces, we're going to be able to answer how much work does force 1. Well, let's see force 1. Force 1 is, sorry, that's a mistake. So this is force 1. So force 1 is that one. So the first thing we need to do is figure force number 1. We have to write it in vector notation. So let's take again the same, and then we see that in the XY free body diagram we could do with only considering force F1, right? This is going like this, so this goes like this, right? This is F1. So I'm taking the entire frame, I rotate it because it's much more comfortable. You don't have to, but if you want, just rotate it. If you don't want, just keep it without rotation. We can do that explicitly now. Here, let's do it also here. It's going to be the same, obviously. The other one will be like saying this, and then saying this, right? These are x and y, and this is also x and y. And now F3, then, excuse me, F1, then will be completely flat, right? That's also F1, and this is F1. So now the question is, well, the work is going to be given by what? Work is going to be given by the component of the force F1 in the direction of the displacement. What is the direction of the displacement? X, or x here. So I need to find what's the component of the force in this direction. What's the component of the force in that direction? So basically I need to figure out that angle, or this one over here. And if I take this diagram, then I know that if I do it from here, this is 30 degrees, right? That's what the problem says. So how much is going to be this angle? Well, that's actually going to be 30 degrees, but we can see it step by step. This is 90 degrees, so this is going to be, that's going to be 60 degrees because it's 90 minus 30, which means that this one is going to be 30 again, which means that this is going to be 60, which means that this one is going to be 30 again. Other way of saying it, make a diagram like this, and so this makes the same triangle as this triangle, right? So that angle is 30 degrees. So that means that for this force, that's 30 degrees. I need to find the component in this direction. What is the component? What's the component in that direction? With respect to the angle, that's the adjacent. So as always, so katoa, which one do we use for the adjacent? We use cosine. So how much is going to be f in the direction of x, or if we wish delta x, because delta x is happening in this direction? How much is that? Well, that's going to be f1 modulus. Let's write it a little bit down here. F delta x is going to be f1 modulus times what? The cosine of the angle, and that's 30. And because f1 is 40 newtons and cosine of 30 is 86, that's going to be about 34 point something, 35. Let's say 35, but the numbers we're not that interested. Okay. Anyway, that's just the idea. We're decomposing the force into that at 0.86. So yeah, it should be 34 actually, something like that. But anyway, 34, 35 newtons. So that's the force. So how much is the work that that force is doing? Well, it's going to be the displacement times the force in the direction of the displacement. How much is the displacement? 0.8 meters. How much is the force? We said 35 newtons. So how much is this? That's going to be 28. So that's going to be 28 newtons. Okay? So, excuse me, 28 joules. So why joules? We have force times displacement, that's newtons per meter, that's going to be the same as joules over here. Because work is a measure of energy. So energy units are joules, work is going to be joules. 28 joules, that's the first question. Let's see another question. Let's see part B. Part B is asking us, and what about force? Well, there's no part B, but that's force 2. How much work does force 2 do? And then we apply the same thing. Work is force in the direction of the displacement times the displacement. So we need to find what's the force in the direction of the displacement. F2 goes this way. So how much of a component of F2 goes in the direction of x? Immediately you see it's 0 because it's perpendicular. But how can you see that? Anyways, we'll use the formula over here. The force in the direction of the displacement is going to be force number 2 times the cosine of the angle. How much is the angle now? Well, the force is going to be pointing down. That will be F2, or this will be F2. So how much is the cosine? It's the cosine of how much is the angle? Excuse me. Now the angle will be 90. But how much is the cosine of 90? That's 0. So how much is the force? 0. So how much is the work? It's 0 times 0.8, which of course is 0 joules. There is no work done on the system by force number 2. And again, it's very important, this sort of grammar, we have to be correct. We do work on a system. Why? Because work is a way of transferring energy. So whoever is applying this force is transferring energy from him to the object. But it only transfers energy to the object if it actually imparts new energy. And what's energy? Energy is another way of accounting for motion. Either motion being actual, that we call kinetic energy, or motion being potential because of the position, that's what we call potential energy, right? So we understand that because an object is hanging high has the potential of using that energy which is stored in the system, which is due to the position, to convert it into motion, because let's say there's a catapult or something like that, and then the object falls and hits and triggers the catapult. So we have converted that, and the higher it is, the more force it's going to be applying at the end, because it's going to be going faster. So that's this idea. If we do not change the amount of energy that the object has, we're not actually doing work on that object, okay? And this force is always perpendicular. There's no displacement vertically, right? Presumably we're just moving like this. So we are not having any impact. And what about force number 3? Let's make it here so we don't have to erase. So what about force number 3? Well, force number 3 is completely parallel to the direction of the displacement. That's to say that theta is going to be how much? 0 degrees. How much is the angle F3 makes with respect to the horizontal? 0. They're parallel. They're just the same. So then in the formula that says that F delta x is going to be F3 times the cosine of 0, which is, this is 1, so that's going to be F3. And how much is F3? 30 newtons. So how much is going to be the work due to force 3? That's going to be that force, which is 30 newtons, times the displacement, which is 0.8, and that's going to be 24 joules. So that's the solution for this problem. We see when forces are acting normal to the object, perpendicular to the direction of motion, there is no component. That's 90, that's 0, there's no work done on the system. When forces are acting parallel, we're applying all the force goes into energy, right? Obviously, depending on how much you're applying it. And when you do it at a certain angle, the only component of that force that actually has an impact on work is the one that occurs in the direction of motion. Another way of finding this one is actually if we add all the vectors together, you're going to see that the net force acting in this direction, the total energy is going to be 24 plus 28 is going to be 52 joules in total. So you can find the net force and calculate what's the work due to this net force. That's going to be 52 because it's the total. Only forces, only the components of that net force acting in parallel, acting in the direction of delta x, are going to be contributing to work in the system. So let's solve problem number 2 on discussions. Now in this case there is a mass of 2 kilograms that it's falling, and it falls for how long? Well, it falls for 400 centimeters, which we know that's 4 meters, right? Centi is 100, so 4 meters. Very good. So how much work was done on it by the gravitational force? So let's say that you're going to observe initial, that's going to be the initial situation, and this is going to be the final situation. And of course we know that the distance between this and that is 4 meters, right, because it's 400 centimeters. And the mass is 2 kilograms. So the first thing is how much work was done by the gravitational force. How much is the gravitational force doing work on the system? Well, then we have to take that object and observe what's the force due to gravitation, that's weight. And how much is weight is mass times g. If we assume in the Earth, that's 10. So that's going to be 2 kilograms times 10, which is going to be 20 newtons of force. And then the work done by gravitation then is going to be what? Well, it's going to be the displacement times the component of the force, which in this case in the direction of the displacement, right? So how much is the displacement? 4 meters. How much is the force in the direction of the displacement? Well, in this particular case, the displacement is happening completely aligned with FW. So the weight or the component is going to be simply the weight times the cosine of the angle. And how much is this angle? That's 0. So that's how much is this? This is 1, right? So that is simply the weight. So how much is going to be the work? Well, the work is going to be given by the displacement, which is 4 meters, times the force, which is 20 newtons. So that's 80 joules of work done by gravitation. And this comes the next question. Okay, and how much says is the potential energy that it lost, right? So we have to see the difference in potential energy. So we're going to calculate the potential energy, gravitational. And how much is that? That's final potential gravitational minus initial potential gravitational. We write a 0 to denote that. Okay, how much is the final potential gravitation? Well, if we could do, we don't know the height, right? But if you remember, potential energy gravitational is defined as mg, and sometimes you will see this written as delta y, or sometimes you will see this written as h. H being the height. So why is that? Because potential energy is always relative. All potential energies are relative because they are in position. Relative to what? Relative to whatever we consider to be the zero potential, as it's called. What's the origin of potential? In our case, we can assume that this is entire height and that this is the ground. So this is something that you can do freely, and then you could choose this height whatever. You could choose this to be 1 kilometer or 1 million kilometers or 0, as we are going to take it to be now, right? Why we take that to be 0? It's just to make it much more simpler, as you will see, but any number will work, because what matters in the potential energy is the difference between before and after, or rather the difference between the current position and what we consider to be the 0 potential energy. This doesn't, it's not that interesting here. In the case of potential gravitational, you will see it. If you leave the object on the floor, it doesn't fall anymore. There's no more potential energy because we take the floor to be a 0 energy. But if you were to dig a hole, the object will keep falling. Why is that? Because it's not really the 0 potential energy. The 0 potential gravitational energy would be like the center of the Earth, right? Which of course is meaningless in this case because that's a singularity. But in our case, we take that to be 0, then we're all solving it. So again, you can take this to mean height, and they're going to be fine for physics 2053, but physically that's not necessarily the case. You will see also the concept of potential energy and actually in potential electric field. You're going to see that concept comes back to this idea. There's forces that change or depend on position, and those ones usually have associated the potential energy. And in this case, because it's gravitational, the source, then we call this potential gravitational. So we can calculate what's the final. Well, the final is going to be mg times final height, which we can just say that's going to be 0, minus, this is 0, right? So this is going to be 0, minus initial. And how much is the initial? If we take that to mean height, that's going to be mass, which is 2 kilograms times, sorry, let me write it. That's going to be mg and then y sub 0. Okay, and how much is mass is 2, how much is that? We can take 10, and how much is the height? That's 4 meters. So how much is this? That's 20 times 8. How much is that? 80 what? 80 joules. So what's the difference in potential potential energy gravitational? 0 minus 80, that's 80 joules. And now, of course, you're looking at this. This is negative 80 and this is 80. What's going on in here? Okay, let's make a system. So what is the work energy conservation principle? The energy conservation principle says that the total energy, the change in total energy of a system, it's equal to work. And if I ask what energies are in here, do we have kinetic energy? We don't have kinetic energy here. Do we have neither rotational or translational? Do we have elastic? There's no elastic. Do we have potential? Yes, we have potential. That's actually this energy over here. And what about here? Well, in here we have no potential, which is what we just saw, and we have, where is the energy going, right? That's going to where? Well, now it's kinetic, so it's going to convert that into kinetic. So it's going from elastic to kinetic. Now the total energy, then we're going to see it's conserved. There's no forces outside. And then we say, okay, if I apply this for the total energy and I consider kinetic and elastic, kinetic and potential, I'm going to see they're matched because there's no external force. Why? Because weight does not count as external force. Weight is integrated through E. But if you isolate that and you only consider the potential energy, you see that there is a change in potential energy. Where is that potential energy going? It's going to kinetic. But why is it going to kinetic? How is applying that? Again, energy is a measurement of motion. How is that thing happening? Well, that thing is happening because there's a force acting on a displacement, which is this idea over here. Whatever I'm losing is because Earth is doing work on the ball. And by doing work on the ball, it's increasing the energy. In this case, it's increasing the energy elastic. So we see over here, if we calculate it, we could calculate the balance of energy. Just calculating balance of potential energy, you're going to see how much is 80 joules. Why is negative 80 joules? Because I've lost potential energy. And where is that energy going? It cannot just disappear. It cannot be vanished. This is the principle of conservation. Where is it going? Well, it's going to another source of energy. In this case, it's going to kinetic energy. But what is the origin, or what's the reason for this? If you were there saying, I have this amount of energy to give, how much energy do I have, can I give? Well, Earth can only give 80 joules, which is the force times displacement that we have calculated for work. This is work done by Earth on the system. So problem number 3 says that there is a car going at 15 meters per second, so the velocity is 15 meters per second, and that's the initial velocity. And it's brought to rest over a distance of 2 meters, right? As it strikes a pile of dirt. So let's assume there's here some pile of dirt or something. How large an average force is exerted by seat belts on a 90-kilogram passenger, right? So it's going to be a passenger here. It's going to be restrained by the seat belt, right? And they're asking, what's the force of the seat belt? Now, why there needs to be a force? Because the passenger is moving with certain velocity, and at the end, I'm just going to make this, at the end the velocity is going to be 0. This is the car. Right now we just abstract car. So the velocity is going to be 0 at the end, and at the beginning is non-zero. And we can analyze the balance of forces and see, and actually we're going to see what source of energy do we have at the beginning. Well, at the beginning we have what? We have kinetic energy translational, but we don't have rotational. Why? Because there's no change in height. And every time you don't change the height at all, even if you are on Earth, you can disregard completely potential energy, potential energy gravitational, because there's no change in height. And so you take whatever height you have as the 0 energy, and that's it. What about the end position? Is the same height, so there's no change in height with it. And there's nothing elastic in here. We're not assuming that the car deforms. In fact, this is a very interesting thing. We can mention it at the end, but when the cars, in the old days, they were thinking we have to make very rigid cars, so you keep people inside protected. What is the problem with that? Is that if you have an object moving with a certain velocity, the car has kinetic energy, but you also have kinetic energy. And at the end of the line of the collision, the car is not going to have energy, but you have somehow to also lose the energy. So how much energy you lose is going to be depending on how much also the car loses. If the car loses nothing, it's kind of rigid, all the energy needs to be lost by you, which means that you're going to be destroyed. So they just realized we have to make cars that actually, when they crash, they don't convert all the kinetic energy, they just don't come to stop, and there is a total force, right? The change in energy is due to work. So if I lose all the energy by means of coming to rest, all the kinetic energy that way, then the force needs to be higher than if I actually am converting some of that energy into another sort of energy. What sort of energy you use in this case? Well, it's elastic energy. So that's why you make the cars to be deformable. When the car comes to rest, as it comes to rest, part of that kinetic energy goes to elastic energy. And so you don't have to rest that much. Not all the force needs to be applied on the human, on the passengers. Energy goes to the chassis, and then the chassis absorbs the heat, and so you don't take much work, that much force applied to come to a rest. Let's see that in this particular case. So in this particular case, initially we only have translational energy, kinetic energy, and we have no other source of energy, and that's going to be 1/2 of mass velocity squared. And what about the final situation? In the final scenario, what we have is kinetic energy final, so this is initial. So final is going to be 1/2 mass v squared, but v squared is 0, so that's going to be 0. Now we're analyzing again the case of the human, right? We're considering the motion of the human. So the human comes to rest with the car. That's why. Why does it come to rest? Because the seat belt is acting on him, it's restraining him. So that's going to be the force that produces the work, accounts for the misbalance in energy. So how much is going to be? That's going to be, what's the mass of the guy? 90 kilograms. So that's going to be 1/2 90 kilograms times velocity squared, which is 15 squared. Whatever that is, and then we just can't say that what's the change in energy. Well, in this case, the change in total energy in this case is just purely kinetic energy. There's no other source. So in this case, the total energy beginning is purely kinetic energy, and the total energy at the end is kinetic energy at the end, purely. What I was discussing before is that what if we added here some potential elastic energy? Then the balance of energy could go not just simply through the 0 here, but also some of that here, right? Okay, as much as possible. Why? We're going to see it in a second. Let's keep that in parentheses here for the time being. So let's go to the total difference in kinetic energy. That's going to be initial minus final, and that's going to be equal to force, to work, which is force times the displacement. So how much is the difference in energy? What's the final energy we're saying? That's 0. What's the initial energy we're saying? Is 1/2 of that. Let's calculate how much is that, which is going to be 10,125. Yep, and then that's going to be equal to negative 10,125 joules, and that's the force times the displacement. Okay, how much is the displacement? We can replace. Displacement we were told was 2 meters. So how much is this? Well, that says that 1025, it's equal to force times 2. What force is this one? Again, what's the force responsible? Obviously, this is not balanced. I'm going from 0 to negative 10,125. So obviously, the energy I had, I'm losing the energy, right? That's why it's negative, right? It's work. So it's work I'm losing. So why am I losing energy? Well, because there's a force acting, a force producing a work. What's that force? That's the force of the seat belt. I was moving, I'm not moving. Why I'm not moving? Because a force is opposing my motion for all this displacement. So that force, of course, is the force of the seat belt, right? So then I can solve for the force of the seat belt, which was the question. And then I'm going to see that that's minus 5,062.5, something like that, no? No, yeah, maybe. So, newtons, 5,000 newtons. So how much is this? Is this a lot or not? Let's say that this is, let's say that this was 5,000, it doesn't matter, right? How much is this? Okay, let's get force of the seat belt and divide by G, which is divided by 10. How much is that? 500, about 500. Okay, so is that a lot or is that much or not? You're going 15 meters per second, which is which is about 30 miles per hour and 50 kilometers per hour. Okay. Okay, so 50 kilometers per hour, so it doesn't sound like a lot, but if we divide the force that we're actually experiencing, which is 5,000 newtons by g, which is 10, I'm going to find that this is equivalent to 500 kilograms. So that's to say we're just feeling someone of 500 kilograms falling onto us for 2 meters. So it's not going to be a pleasant experience, right? To say something. So obviously that's a problem, right? So how do we avoid this issue? Well, if instead of stopping in 2 meters, you were to stop in 4 meters, then you will need, instead of 500, 250 newtons, 250, right? Times g, so 250 kilograms equivalent, which is more doable. And if instead of 2 you had 10, which is 5 times more, you will need only 100 kilograms, which is again is much more understandable. What's the problem here? That the more that we increase the displacement, the less of a force we need. This is kind of equivalent to what we were discussing with impulse. Impulse is a force times time. The more time of interaction, the lesser of a force you need to actually to produce the actual impulse that you need to account for the difference in a state of motion. In this case, how do I account for the difference in energy? Well, we need to be a force and times the displacement. If we make the displacement small, the force needs to be higher. If you want a lesser of force, then make the displacement longer. This is another way of saying that. But let's see also another thing that we can see in here. Let's say that for the purpose, well, this is the answer to the question, right? But let's say, and why, by the way, why is it negative? Because the force is obviously acting opposite to the motion. So it makes sense that the sign is negative. If it was not negative, we should be concerned about something. Let's say now that actually we are accounting from the fact that the car is compressing, right? And let's say that it compresses, I don't know, like 50% of the car compresses, or 30% or 20%. Let's say 25% of the car compresses. So then we're going to have that in the final scenario. In the initial, we have potential elastic is going to be to 1/2 of k delta x squared. But because it's at rest, how much is going to be the elastic potential initial? We can erase this to make it more obvious. Let's go step by step. So potential elastic initial is going to be 1/2 of k delta x squared, okay? And so how much is the change in elastic, what's the deformation? This is here. What's the deformation at the beginning? Nothing. The car is brand new. It's perfect. So how much is this? This is 0. So how much is this? 0 again, right? And we see another example where the potential energy is always relative to something that we call the zero potential energy. What do we call zero potential elastic energy for the car when the car is in pristine condition? If we deform it, because we compress it, or if we were to stretch it somehow, then we would be increasing the potential elastic energy. The car now has the energy to go into motion, which is elastic because it needs to recover, right? Or it wants to recover because of Hooke's law. Okay, so there's zero potential. What about the final? Well, in terms of velocity, we're having zero velocity, so that's going to be translational, excuse me, and that's going to be 1/2 mass v squared. And of course, we know this is 0, so elastic kinetic is 0. But what about elastic? And here's the thing. If we, okay, I said 25%, but it doesn't matter. If we get some of this energy, which is going to be 1/2 of k delta x squared, we don't even need to put numbers, right? But let's say that this is different from 0. Why? Because now this is different from 0. Now we have a real deformation. We have changed the amount. It doesn't matter if you stretch it or you compress it. It's squared, so the negative value, the minus will go away. So because I compress it, now I'm going to have a certain amount of energy that gets into compression. So I don't go from fully kinetic to no energy. Now I go to fully kinetic to no kinetic, but some elastic, some potential. So then what that means is whenever I come to my balance of forces now, excuse me, whenever I come to my balance of forces, now I'm going to have 0 minus this. I'm going to have something which corresponds to the potential elastic minus 10,025. And so this number is going to be larger than minus 10,025. Let's say it's 8,000, okay? Just for the purpose of this example, minus 8,000. Now the question is how much force is doing my seat belt on me? Because now it's minus 8,000, then I can see minus 8,000 is going to be equal to work, which is force times displacement. So now I'm going to have the minus 8,000, it's equal to force times displacement. Displacement is 2 meters, which means that the force now is going to be how much? 4,000, right? And then if I go here, I'm going to say that's equivalent to 400 kilograms. If instead of this something, I make it larger, instead of 2,000, I just made it here, 2,000 joules, right? Let's say 4,000 joules. which, by the way, for that you would have to have twice the same compression, right? Because this goes with the square. So if I have to have, excuse me, square root of 2 in this case. So if I want to have twice as much potential energy, is because I have a square root of 2 of this, because it goes to square. But let's say that if instead of having whatever this deformation I had on the car, I have twice as much deformation, that's going to be twice as much, so it's going to be 4 times more, so I'm going to have 8,000 joules. So eventually I'm going to have 2,000 joules to release on the force, and the force is going to be then responsible only for 1,000 joules, which means it's going to be the equivalent of 100 kilograms. But at the bottom, at the end of the day, excuse me, that's going to be 400 newtons. So look what we just did in here. At first we said that the force, and we can write it in here, the force responsible for this, oh excuse me, that's 4,000 newtons. The force responsible without elastic energy was 5,000 newtons. Now I'm saying elastic takes care of 2,000 because of the deformation of the car crashing. Because the car is crashing, now the force required is less. And it makes sense. That's why they've used in modern cars. Modern cars are not rigid as in the old way where you just hit the thing and the entire thing goes to you, meaning you need entire force to account for that. Some of that energy goes into the car, then that energy, it's released from your system. You don't have to account for that, which means that the seatbelt is not going to be applying that force. And so you're not going to be needing to apply such a huge force, which means that you have a chance to survive an accident. And listen, by the way, how much of force we're doing, which is 5,000 newton, which again is equivalent to 500 kilograms, to stop at a 50 kilometers per hour or 30 miles per hour. So this is sort of what we would say very slow speed. But if you actually crash and come to stop in 2 meters, that's a huge force. So very little velocity many times is enough to kill you. So not to speak about 100 miles per hour or 70 miles per hour. If you're in the highway and you hit something at 2 meters per second, 0 chance of survival, like 0. So that's very important to count. Many times we just don't have that idea. If you now use conservation of energy, you can figure out how much energy you need to lose, and then you can calculate how much is that force, and then imagine yourself sustaining someone of 500 kilograms on top of you for 2 meters. Is that something that you can survive, or is that something that completely destroys you? And right? So that's the kind of question that you need to see. And you could make the same argument also for internal organs, right? Because you come to stop, the seatbelt is restraining your body, what happens with the things inside, right? So that's another problem. Even if your body might be okayish, inside you're completely destroyed. So it's important to account for motion also when driving the car, to be responsible, not to drive recklessly. But also we see here was the idea of car designers when they just make elements that are deformed. Something similar with the airbag, because now we have the airbag is elastic, some of that force also is going to be absorbed by the airbag. So we have something that is taking energy from us. We're not just simply going from some kinetic to no kinetic now, because we have the airbag, because we have the car that is deformable. All those safety elements are going to be taking some of that energy, so that energy does not need to be dissipated anymore in terms of work from the seatbelt. And so again, we have a chance for survival. Problem number 5 says there is a block of 500 grams shot in an incline of 25 degrees. Let's say that the incline goes like this, and then you shot something here, and the angle is 25 degrees. With an initial speed of 200 centimeters per second. So the initial velocity is 200 centimeters per second, which of course is 2 meters per second. Always convert to international units to avoid issues down the line. So how far up the incline will go if the coefficient of friction between it and the incline is 0.15. Now what's the coefficient of friction? Is this one they don't say, but obviously it's kinetic. Why is it kinetic? Because the object is moving. So every time an object is moving, I know immediately I need to use kinetic friction, excuse me, and not the static friction. Static friction is what's saying, is it going to be moving or not? Obviously, when the incline is moving, it's moving. So kinetic friction. Now we're going to see this, and we're asking how far will it reach before it comes to 0, right? Now, if the subject is going up, we could do the free body diagram and observe what's the deceleration, which is going to be a result of the weight opposite the weight and the friction. So I'm going to have friction, and I'm going to also have weight in here, right? Opposite to that motion, and I also have the normal component in here, right? So and then there's no positive force. It's just simply velocity. So because it's going to be a net negative force in this direction, then I'm going to find, if I do free body diagram, that the object will come. But instead of doing that, I can analyze what is different between these two positions here and here, between the initial and final position in terms of energies. So the initial, which is here, is going to be what? Well, the object is going to have kinetic translational energy, and that's how much? Half of mass half of mass velocity squared, and that's going to be, do we know the 500 grams. So the mass is 500 grams. Okay, and so how much is this? That's going to be half of the mass, which is 0.5, so it's 1/2 of 0.5 times velocity squared, which is going to be 2 squared, so that's 4, 2, 1. So that's 1 joule, right? And then we have, what else do we have in here? Well, we have nothing else. There's no other source of energy. Okay, and now what is the final scenario? Well, the final scenario, I'm going to have this. And I'm going to observe that the object is in here. And what's the final velocity? That's 0. So what is the translational energy? That's going to be 1/2 of mass v squared, and that's going to be 0 joules. So is that all? Then if this was all, then I would say, okay, the difference in kinetic energy is just simply due to friction. But here's the important thing. The object is not just simply going sideways. It's also doing what? It's increasing its height. If I drop the object, it will come to rest, but then it will come down. Why does it come down? Because it has stored part of that kinetic energy into potential energy. It has changed its height. So then I have to figure out that in real there is gravitational potential energy. In here I can define this as to be the 0, and so I'm going to have 0. But of course I know that there is a height. Now here's the thing, however, that we need to see. If we define the height from here to here, right, how much is going to be there? And that's a matter of trigonometry. So let's make this diagram, and let's say, okay, the object is here and it used to be here. When it was here, this is 0. Now it's here. How much is this height? Well, I'm going to know how much is this, because how much is that? That's the displacement of the object. And how much is that height? Well, if I know this angle, I know that this is the hypotenuse, this is the opposite. And whenever I have opposite, I need to use what? So sine. So then I know that the height, or the delta y, the opposite, the hypotenuse, which is delta x, times the sine of what? The sine of 25 degrees. And that's going to be, well, we don't know how much is delta x, but we have that. So when we come here and say what's the change in potential energy, that's going to be this, which is of course 0.5 times 10 times whatever this is, right? Which is delta x times sine of 25 degrees. Okay? So now what's the total energy at the beginning and at the end? Well, the balance of total energy is going to be final minus initial. Let's write the final. The final is given just simply by this, which is 5 times delta x times sine of 25 minus initial. How much is the initial? Well, that was just simply 1. And this is going to be non-zero, because the only way to be 0 is if delta x is 0, but that just remains in position, and we know that's not happening. So there's going to be a misbalance in energy. When that happens, why is that? Well, that's because you have a work. But what is the force doing work? And you could say, well, there's gravity. But here's the thing. Gravity is already included through potential elastics, so that's not anymore something to account for. What is that? That's going to be friction. So what force is that? That's friction acting on a displacement. And what, by the way, it needs to be the component of friction in the direction of the displacement. But friction is always in the direction of the displacement, so we just don't need to even write it if you don't want. Friction is always in the direction of the displacement, right? So how much is going to be friction? Well, friction force, we know, is mu k times the normal force, right? What is the normal force? The normal force comes from free body diagram making the weight component into the y. So actually we have to solve for that. So let's put that box in here. So we put that the weight is coming here. So I need to say that the balancing forces into the y, you can do this explicitly. Basically the balance of forces into the vertical component is going to be equal to what? To the normal force minus the weight into the y component. How much is the weight into the y component? That's going to be mg times what? Mg times, this is the y component, this is 25. So how much is this one? This is the adjacent, so is that cosine of 25. And so that's equal to mass times acceleration in y. But how much is the acceleration in y? Is 0, because it's not changing in y direction. Y being this one, okay? That is y. That's y, and this is x. So this is going to be 0, which means this is 0, which means that the normal force is just simply mg cosine of 25. And so that means that the friction force is going to be 0.15 times mg, which m is 0.5, G is 10, and cosine of 25. And if we calculate this number, that's equal to, so this is going to be equal to 0.68 newtons. And so we can come back here and write, and how much is 5 delta x sine of 25? 5 times sine of 25 is 2.11, so that's going to be 2.1 delta x minus 1, and that's going to be equal to F friction times delta x. Friction is 0. Let's write this thing here. So we say friction times displacement, so we can just use this line. So that's going to be 0.768 newtons times the displacement in x. And so we just need to solve for displacement in x. That's going to be 2.1 minus 0.68 delta x, and that's equal to 1. And so delta x is going to be 2.1 minus 0.68 is going to be 1.7 approx, 1.4 approx, and so that's going to be 1 divided by 1.4. And that's going to be equal to 0.71 meters. So how long does the thing go? It's 0.71 meters. Why? Because there is friction. If there was no friction, of course the entire kinetic energy will convert into gravitational energy until you exhaust everything. And so we will find directly from here that delta x would have to be 0.5, which is 5 times sine of 25, which we saw is 2.1. Because there is friction, you don't stop 2.1 meters. Because there's friction, you stop at 0.71. And the higher the kinetic, let's write that thing here. Friction is kinetic times normal, right? Normal is going to be the same. It just depends on the incline. But for the purpose of this example, the higher that this is, the higher that this is, and therefore the higher than the work is going to be, which is friction times displacement. So the higher the kinetic static coefficient of friction, the higher the friction force, which means the higher the work, which means in the balance of energy, less of my potential energy is going to go, less of my kinetic initial energy is going to go into the potential final energy. And so that means I'm going to reach a lower height, and that's trivial. If this is very if this surface has a very high kinetic friction, it means it's going to have a lot of friction, so you will stop earlier than if actually this is frictionless. How far would it reach if this was frictionless? Well, if this was frictionless, meaning mu sub k being 0, the friction force will be 0, and so the work will be 0, which means that the total energy needs to be conserved. The difference in energy is 0, because this will be 0, which means initial energy is equal to final energy. How does it translate into here? Well, it will translate into saying that the total kinetic energy would go into potential gravitational. So 1 joule needs to be accounted like this. And because this is 1 and this is 0.5 divided by 2, that means that will be times the sign, of course. That will be 2 times 0.25. We said this is 2.1. So that would be delta x. So I think 3 or 4 times more, no? Something like that, just calculate it. But basically, all the kinetic energy goes to potential energy. Why doesn't go to potential energy in this case, in the system? Because there's external work. Who is doing external work? Well, that's the ramp, which is applying a friction. And because it's applying a friction, energies are not balanced. There is a misbalance. That misbalance is due to work, which is due to the force times displacement, which is due to the friction force. The higher the friction force, the smaller the displacement. And if friction force is 0, then displacement doesn't matter, because there's no force anymore, so there's no more work. If there's no force, there's no work, right? So this is just to say that we have a displacement which is less than it would account if we only were accounting for conservation of energy. Conservation of energy is broken. Why is it broken? I mean, it's broken. There's no energy at the beginning and at the end. It's not the same. Why is not the same? Because there's work. And so that's friction extracting energy from the system. And if we remove friction, then we will be reaching farther away. But this also can be applied conversely. Imagine that instead of being a ramp, you're in a flat surface. If there is friction, you come to stop. If there is friction, you come to stop earlier. If there's no friction, you come to stop much later. So you can solve this problem for a flat surface. And then you will see that how, for instance, when it rains, when it's wet, when it's snow, when it's icy, this kinetic friction is going to drop. This coefficient of friction is going to drop. If it drops, means that there's going to be less and less work. If there's less and less work, then means we're going to need to have a longer distance to come to stop, which is also why when you're driving, your safety distance needs to be adequate for the different driving conditions. But again, from the point of view of the system defined as just simply the block has certain kinetic energy at the beginning, that's its total initial energy. At the end has less than the initial energy. And we know at the end we only have potential elastic, and so potential gravitational. And so why is this the case? Well, because there is an external force, and that's the force of friction. So now we can solve problem number 10 in discussions. So it says that there is a dart of mass, this is 0.1 kilograms, and it's pressed against the spring of a toy gun. So let's say that this is the spring of the toy gun, right? This is supposed to be inside the muzzle, but anyways, let's see, this is the thing, and here's the trigger, and not that bad. Okay, and so you're compressing this thing, and the spring has a stiffness of 250 newtons per meter, which is equivalent to say we're going to have to apply 250 newtons to achieve 1 meter compression, which of course is crazy in this context. And it's compressed. How much is compressed? It's 6 centimeters, which, as we know, that's 0.06 meters. And then it's released. So we compress it at 0.06 and then we release it. And if the dart detaches from the spring when the spring reaches its natural length, so basically it just goes all the way to full, what speed does the dart acquire? Now, it's an important thing to see also in energy conservation that this is the same as linear momentum and angular momentum. We have to be careful in what we define as our system. Before we were seeing the car and we were saying, well, the total energy of the car and the total energy of the person, if you take some of that energy in the car because it deforms, you don't get it into the person, so the person doesn't need that much force from the seatbelt to restrain it and blah, blah, blah. This is going to be something similar. Now we're going to have to consider what's the scenario, what's the situation before and after. At the beginning, we're going to have the gun, and the gun is going to have the spring, and this is the dart, right? And then this is compressed. So in reality, I don't even need the gun anymore. I can just make a system. Let's do it more clear. That at the beginning, I'm going to have spring compressed and the dart. And at the end, I'm going to have the spring released and the dart. And I'm making the dart slightly separated from there, but it's supposed to be in the instant that they just break apart, okay? So then I can say, what's the total energy in here? What do I have in terms of the dart? There's no energy at all. Why? Because the dart is not moving and the dart is not being deformed. So the system is now like dart plus spring. This is what I need to account for. This is my system. Because if I only consider the dart, I'm going to see the dart is not moving, and so the dart is moving at the end. And so I'm going to see there's a change in energy. Whenever there's a change in energy, it's going to be a work. Who's doing that work? Well, that's the elastic force of the spring. So I could do this and then just find from the elastic force how much is going to be the elastic force and all that, but I'm going to be missing some components because I don't know how much. Well, it's going to go all the way to restoring force, so that will be another way, right? Instead of doing that, what I can do is just consider the entire system containing the dart and the spring. And so what I can see is that the kinetic energy at the beginning for both of those is 0, for both the dart, and so we would have to have kinetic energy translational initial is going to be kinetic energy translational of the dart, right, plus the kinetic energy translational of the spring. But both of those at the beginning, both of those are 0, so that means there is no kinetic energy. What about other forms of energy? Well, what about potential elastic energy at the beginning? Well, I'm going to have a potential elastic energy of the dart, and I'm going to have a potential elastic energy of the spring, and both initial. But how much is the dart? 0. The dart is not being compressed, only the spring is being compressed. And how much is that? That's half of k delta x squared. And because I have the numbers, I can replace now. That's going to be 1/2 of 250 times the compression being 0.06 centimeters squared. Why? Okay, that's 36 times to the minus 4, so that's going to be 25 times 36 times to the minus 4, and that's going to be equal to how much? 0.45 newtons. Let's go to the situation at the end. What do we have at the end? I'm going to have kinetic translational energy, which is going to be kinetic translational final because of the dart, plus kinetic translational final because of the spring. The spring is not moving at the end, we just assume it just releases and stays. In real world, usually they oscillate a little bit. In this first approximation, we can disregard that. We always work in physics not analyzing exactly the situation because that's always impossible, but making several approximations that are meaningful. So if the spring is stiff enough, probably we just release. And yeah, if it moves a little bit, but not that much, we can just disregard that contribution. And then we have potential elastic at the end. And how much is going to be the potential elastic at the end? Well, because I have a system composed of those, I'm going to have elastic because of the dart, and I'm going to have a potential elastic because of the spring. How much is the potential elastic because of the dart? The dart is not being compressed at the end, so it's 0. How much is the potential elastic of the spring at the end? That's going to be also 0. Why? Because once it gets released, 1/2 of mass, 1/2 of k delta x squared. But delta x, when it's released, x final is x sub 0, therefore delta x is 0. Therefore, there's no potential elastic energy at the end. So that's going to be how much? That's going to be 0. So if I calculate that, what I'm going to find is that the total energy is going to be the final energy, the total energy at the end. Total initial, that was 0.45 joules. Excuse me, that's not newtons, that's joules. And how much is this going to be the total energy at the end? Well, the total energy at the end is going to be equal to 1/2 of mass final velocity square, and that's it. Which, because the dart is 0.1, that's the mass of the dart, right? That's going to be 0.05 times v squared. That's the total energy at the end. And so I say, okay, how much is this velocity? Well, I can use it because of accounting, because now I'm going to say the change in energy is going to be due to work. What forces are here in action? And again, you could say gravity, but everything is at the same height. So gravitational is not going to apply at all. It's not going to change anything in this case. So what's mattering here? Now what matters here is elastic, but elastic is accounted for because of the potential energy. So in reality, we don't have any other forces acting here. We could have air friction. We're not considering friction, so the forces here are going to be 0, right? It's going to be 0, which means there's 0, which means that the initial energy needs to be the same as the end. In other words, energy is being conserved in the system. And energy is conserved in the system. That means needs to be equal to that. So that means that 0.45 needs to be equal to 0.05 times v squared, which means the v squared is equal to 0.45 divided by 0.05, which is going to be 9, and that means that v is equal to the square root of 9, which of course is 3. So, yeah, 3 meters per second. So you see, if we were analyzing this from the point of view of work, we could do what's the compression and then just multiply times the displacement being 0.06, calculate what's the force, etc. There is a problem if you do that, however, is that the force changes with the displacement. And in physics 2053, then you would have to use the average force, let's say, which is divided by 1/2, which is why we have this 1/2 over here. So solving this from the point of view of work is not easy. You're going to have a factor of 2 that's not going to be accounted for. If you are actually integrating, that disappears, that's not a problem, but because we don't use differential calculus, going through the root of work, it will be difficult. What do I mean by going from the root of work? Is just analyzing, for instance, the dart. Other thing that you could say is there is a force applied onto the dart for amount of time or of a certain distance, and then let's see where it ends up. With accounting energy, we solve all that problem, just seeing whatever energy is at the beginning is at the end, but important. Whatever energy we have at the beginning in the system needs to be the same at the end in the system if there is no external forces, meaning there is no work. And if you consider your system only to be made out of dart, then this seems to be a problem. Why? Because the initial kinetic energy is not the same as the final kinetic energy, and there's no other source of energy. What's that work coming from? Well, that's coming from the spring, which in your definition of the system compressing only the dart, that's the spring. But if you consider the dart and the spring, then this is beautiful, it solves easily, and then we solve the problem. Once we know the initial velocity, then we could say, oh, how far it reaches. And even based on this, you could just calculate different compression rates, and calculate how long would it take to fall, where would it get. You can then make this much more. You could use then kinematics and keep solving the problem, right? Or keep using conservation of energy and saying, okay, if at this point this is here, what happens when the dart touches the ground? And if they tell you how high it is, then you use conservation of energy, and now we are going to have potential gravitational energy to account for that difference, right? So again, this is just an accounting approach to physics problems, which is the entire idea of energy. Energy is trying to somehow capture how much amount of motion there is, but not just simply how much motion it's expressed right now. which is what usually happens with linear momentum, but also what happens when there's an amount of motion that is not expressed yet, it is potential, and then it gets actualized. So why is it potential in the spring? Because it's compressed. Why is it potential in the apple on the tree? Because it can't just fall and convert it into motion. But at this point it's not expressed, but it is stored in the system. Why is it stored? Because of a force that depends on the position. That's the idea, and this is just a beautiful example of how we can solve problems that otherwise might be a little bit more complicated, because we have many different elements. We just solve them if we go step by doing an accounting of how much motion there was at the beginning and how much motion there was at the end. In physics 2053, as we said, we're only dealing with 4 types of energies, which are going to be kinetic translational, kinetic rotational, potential elastic, and potential gravitational. And again, balance of energies. Analyze if there's anything external to the system that is applying a force onto the system, or if it's extracting work from the system, right? If we had a log of wood and we were considering maybe heat energy or chemical energy, we could release that and then take it out in the form of heat, right? That's when you do a bonfire to warm up. Well, you don't have the same energy at the beginning and at the end. Why not? Because there's work extracted from the system in the way of heat. But if you were just yourself in that thing and you are absorbing all the heat, if you include yourself in the system, that needs to be the same, so that will be 0 energy. And that's why we say in the entire universe, everything considered, there's nothing outside can change anything inside. So the universe needs to conserve energy, because otherwise energy is materializing. And if energy is just materializing per se without a reason, then we would have to rethink the entire physics. But if energy means what we think it means right now, which of course there's a footnote in there saying, assuming that this is correct, that cannot happen, because it's a principle that goes before physics, right? That's one of the presuppositions that we studied in chapter 0 or in the introduction. But anyway, just again, what's energy? Sometimes an elusive concept, but energy is related to motion. So we have to count every type of motion there is, rotational, translation, and we also have to count for potential motion that's not expressed yet, but because of the position of the object is somehow stored inside the system. It's not because of the system, it's because of the position that the system has. And in future courses you can study other sources of energy, chemical energy, biochemical energy, heat, which is a way of transferring energy in thermodynamics, thermal physics, and electromagnetic energy, which is energy for the light, energy of electric and magnetic fields, and so forth, different sources of energy. But again, accounting principle, and with accounting principle we solve problems very easily. So let's solve problem number 12 from discussions. So it says there is a ball, a ball at the end of a pendulum. The string has 108 centimeters of length, and the ball speed is going to be 400 centimeters per second. That's the velocity at this point, right? And we want to determine at what height above the lowest position will it rise before stopping. And the second thing is, what angle does the pendulum then make to the vertical, right? Or actually, if we go here, say this one, so that's going to be the angle. Now, one of the things we say is, first of all, this diagram is wrong. Why? Because whatever energy I had here is going to be potential energy. That is going to convert here into kinetic energy. And then the kinetic energy is going to be reduced to go to potential energy. That potential energy in the absence of work needs to be the same at the beginning and at the end. And so the height is going to be necessarily the same, because we're not losing the mass and we're not losing anything. So in reality, where are we throwing it, where are we reaching, or where are we throwing it should be symmetric. In the real world, it's slightly not symmetric because there's friction, there's losses from drag of air and this and that. But basically that's the idea. It needs to go up to the same height. In any case, we just can't solve this problem, as we were just hinting to, and this is this chapter anyways, with conservation of energy, which solves things much more easily. We did this problem also without conservation of energy. The first thing is just to realize the initial velocity is 400 centimeters per second. We need to convert that into international units. That's 4 meters per second. The length of that pendulum is going to be actually the radius of curvature, and the radius is 180 centimeters, which in international units is 1.8 meters. So this is the information that the problem provides in the international unit systems. So what is the thing that we need to say? Well, we have initial and final conditions. What's going to be the initial and final? Now, let's say initial is when the pendulum is here, and the only thing I observe is that the pendulum has certain velocity. So what only thing I have in the total energy at the, and the total energy at the beginning, that's going to just be purely translational kinetic energy at the beginning, and that's going to be 1/2 of mass v squared, and replacing, we're going to find, do we know the mass of the object? We don't, so that's going to be 1/2 of the mass and the velocity square, which is it's going to be 4 meters per second square, right? That's 16, so that's 8 times mass. That's the kinetic energy, which is the total energy at the beginning. What about at the end? Now at this time, velocity is going to be 0. So what has changed? The only thing that has changed is the position. And every time we have a change in position, it's good to see, am I changing the height? If I am, I'm going to have potential gravitational difference. I am changing the position with respect to something elastic. I am deforming something. If I am, then I should have potential elastic. In here, the string is assumed to be ideal, and so it's not going to be stretched or compressed. The only thing I'm changing is actually height. How much is the height? Well, that's actually kind of the question in here, right? That's going to be saying at what height above the lowest position will it raise before stopping. If I take the lowest point as 0 potential energy because I didn't include it here, then the total energy at the end is necessarily only potential energy at the end, and that's gravitational, and that's mg delta y. Remember, delta y is because we refine it with respect to something, but this is just simply height, so use whatever you prefer. And in that case, that's what we're trying to solve for, so that's going to be mass, that's going to be 10, and this is going to be delta y, which is what we're trying to figure out. And if you want, you can call that h, it doesn't matter, let's call it h, but we call it h. Why? Because if we define delta y to be this the 0 level, then that's 0 here. That's going to be y sub 0 minus y sub 0. That's 0 component of potential gravitational, but not 0 here. And how much is delta y? Delta y is h, because this is going to be, delta y will be h, delta y is y minus y sub 0. If I take y sub 0 to be 0, then that's going to be y, and that's h, so that I see it. Whereas in here, if I take y sub 0 to be 0, then delta y here is going to be y minus y sub 0, but here is y sub 0 is the position, so obviously that's 0, so there's no potential contribution in here, right? So once I do that, I can just say what is the change in energy, and again, as always, the change in energy, it's necessarily equal to the work. Now, is there any forces acting in here? There are no forces in here, so that's going to be equal to 0, which means that the total energy needs to be conserved at the beginning and at the end. So now let's make the balance of energy in this case. So we're going to have the total energy, it's going to be m times 10 times h, and that needs to be equal to what? It needs to be equal to initial, which is 8 times m. Now, of course, from here m and m cancels, and so we see that h is going to be 8 divided by 10, which is 0.8 meters. So how tall it reaches is 0.8 meters, right? That's h. Okay, in the question B, it's going to be asking what angle does the pendulum make to the vertical, and so we can figure out basically that through geometry, right? Let's erase here quickly. So let's see quickly that one. We're going to have the ball here and the blob here, and we know that this is radius, and then we know that this is h. And as how do we solve for the angle theta? Well, we need to use trigonometry. But the first thing to realize over here is that this height is going to be radius minus h. And if we see that, then the triangle becomes this. Radius minus h, and angle theta. And then obviously it says, what is this angle with this side, with respect to the angle? That's the adjacent. So what do I use? That the cosine of theta is equal to what? Adjacent divided by hypotenuse. That's 1 minus h over r. We have h, which is 0.8, and we have r, which is 1.8. And that's going to be slightly less than 0.5. So total is about 0.56. And so we say that the cosine of theta is 0.56, which means that theta is going to be also 56 degrees. So we will go all the way up to 56 degrees to complete the motion. And so we have analyzed this situation or this scenario again from the counting principle of energy. If you count for initial energy, if you count for final energy, it needs to be the same. If there's no work, then energy needs to be conserved. Initial and final need to be the same, and from that you can figure out pretty much any problem of the ones that we were solving before with kinematics, but much more conveniently. So problem number 14 is telling us there is a motor running at 20 revolutions per second, so we can say 20 revolutions per second, and supplies a torque of 75 newtons per meter. Now we want to know the power. And what's power? Well, power is the change in energy over time, or work over time, because change of energy conservation principle is equal to work. Why is power interesting? It's more interesting in applications. You need to do a certain amount of work in a system. Whether you do it fast or slow is going to depend. It's going to be described precisely by power. And as we just mentioned, power is actually just the change in energy over time. It's the equivalent of saying the velocity of change of energy in time. We said the velocity is the velocity of change in position in time. How fast position changes in time. Power is going to be how fast energy changes in time, which of course is going to be given by the difference in energy. How much energy changes is the work, and that work over time is what we define as power. Now this is a rotational motion, which is going at 20 revolutions per second. So the first thing to do, of course, is to convert. Remember, the 1 revolution is 2 pi radians. So we have to convert the revolutions to radians, and that's of course going to be 40 pi radians per second, where we have 20 times 2 pi, that's 40 pi radians per second. So now we have international units, and we're all okay. Now, how do we connect these things to power? You have the formula anyway, but just to see it, power is work over time. But what is work? Work is force times a displacement over time. And how much is displacement over time? Well, that's velocity, so that's force times a velocity. And if I'm talking about circular motion, then there's two ways of saying that. Well, we said that linear velocity is equal to omega times the radius of the circle being described. So then I can go back there and see, wait, I can have the power is equal to force times omega r. And if I rearrange that, I'm going to see that I have force times radius times omega. But what is force times radius? Well, that's actually torque. So then I can see that the power is actually torque times omega. So simply calculating torque and having omega, we can find, having torque and the angular velocity, we can find the power. So in this particular case, the power is going to be just simply 75 newtons per meter times 4 pi. And that's going to be 300 pi watts. And the funny thing here, the historical thing, is that originally when steam engines were introduced in the Industrial Revolution, they were trying to show that these machines were much more powerful than a horse, or actually several horses. So they made up this unit, which is how much power can a horse actually output, produce as an output, and then divide and then show, give the result in terms of that. So let's approximate this. If we say that pi is 3.1, that's going to be 930, something like that, watts, right? So we actually just write W, and then we should be good. Capital W, units belonging to a person in capital. So we need to go from 1 watt, it's 7, the other way actually. So a horsepower, that we can just write HP, is 750, let's say, approx watts. So now we need to say, how many horsepower is that. So we have 930 divided by 750, which is going to be 1.2 something, 1.2, 1.3 approx, right, horsepower. So if we are asked how much power is this engine outputting, it's 1.3, about 1.3 horsepower. That means if you had a horse competing against that, 2 horses will be better than this engine, kind of idea. That is just simply a unit that was introduced for the purpose of making people understand how powerful was a machine, and of course was introduced with marketing in mind, right? Still as used nowadays. You see your cars, you're going to see they're going to provide the torque, and they're also going to give you the power when you see the specs of a car or a motorbike. And that's going to give you how fast it's going to accelerate, but also how much power is being capable of outputting. Which means the truck, you're going to want to have a high power so you can carry a lot of weight, and how fast it accelerates and everything, you're going to also have it through torque. So this is just an idea of power, energy, put it in time, how fast it goes or how slow this happens, how fast or slow this engine is outputting energy, and then another unit just for curiosity. So in problem number 15, we're being told that there is a uniform sphere that rolls on a horizontal surface at 20 meters per second. And then it's going to find an incline with no friction. What will be the value of the height where the ball stops? So this is similar. This is half of the experiment that Galileo did with the inclines, right? Now we know, because we studied that anyways, in reality the positions that we're going to be interested in is this time is going to be the initial, and there's going to be a time where the ball comes to rest, which is going to be the final. So these are the two scenarios that we want to study. Why do we consider it here? Because the ball is going to be moving. In the absence of friction, velocity here and velocity here is going to be the same. Remember, that was the argument we made with introducing Galileo. The arguments Galileo introduced to describe this. As the ball goes down the ramp, it gains velocity. Acceleration is larger than 0. As the ball goes up the ramp, the ball loses velocity. Acceleration is negative. But what happens when it's neither gaining nor losing? Well, acceleration is 0. And that's actually this case, because acceleration is 0, velocity is going to be constant. So it's going to reach all the way up to the beginning of the ramp or the inclined plane with the same velocity. So we know the initial velocity is still going to be v sub 0. What else do we know? We know that whenever the ball reaches the height, that's going to be the maximum height. That's going to be the case where the velocity is 0, because it comes to a stop. And at that point, it's going to come in downwards. Why? Because gravity is going to be pulling it down. Okay, so we know that, and now that's the two things that we know from this problem. The question now is, what will be the maximum height, right? So we could do kinematics, we could do this and that, balance of forces, or we can use conservation of energy approach, which, as you will see, is going to be much more easier. So let's start analyzing the initial situation. What is the initial situation in terms of energy? What energies do we have? So the total energy at the beginning. Well, we have certainly kinetic energy, so we're going to have kinetic translational energy at the beginning. And what else do we have? That's pretty much it. We don't have any other information on what do we have in here. Is that so? Well, this is the thing. This ball is supposed to be rolling. So it's not just simply translating. It's not just a solid object that moves this way. And because it's rolling, you're going to have to account for the fact that there is then rotational kinetic energy. It's energy because the object is rotating. It's not the same if the object just slides as if the object is rotating. Now, a good question will be, how can it rotate? Well, let's say someone spin it first, and then conservation of angular momentum, I guess. But anyway, we'll see why this ball is rolling in this surface. So we have that scenario here. We need to find those numbers. So how much is the first one? That's 1/2 mass velocity square of sub 0. How much is that? It's going to be 1/2 mass and then omega sub 0 square. Let's go to the final scenario. What's the final scenario? So the final scenario is that the ball has gone all the way up. Is there any kinetic energy? Well, there's no kinetic energy because the ball is not rotating and the ball is stationary. So we don't have kinetic translation and we don't have kinetic rotational. What do we have? Well, it has gained certain height, so we're going to have is is potential gravitational. And that's how much? That's going to be mgn delta y, where delta y, again, remember, that's the height. And in this case, if we take to be this 0 potential energy, that's going to be height. If you don't take this to be potential energy 0, you'd say this is 10 joules potential energy, that's going to be the difference from here to here, and then you're going to have to subtract anyway 10 joules. So you're going to have plus 10 joules, and here you will have also 10 joules. So that's why I say you can't use any reference for potential energy. And we choose that to be 0 potential energy, that's why we never add, we said plus 0 potential energy. There's no potential energy here. But here we don't have kinetic, we just have potential energy. Now we know there's no other forces acting in here. Again, there's no friction, so work is 0. And because the change in energy is equal to work, if work is 0, that means the change in energy is 0, which means that the total initial needs to be the final energy. And so we can use that to say that 1/2 mass v square sub 0 plus 1/2 mass omega square sub 0. By the way, I made a mistake here. That's not the mass, that's inertia, moment of inertia. Right? That needs to be equal to mg delta y. And now we can replace the numbers. Now, for a solid sphere, this should have been said anyways in the solution. We can take that the moment of inertia, it's equal to 2/5 of mass radius square. Right? Radius being, the radius of the sphere. What else do we know in here? How much is omega sub 0? Well, we know omega sub 0 from the relationship between v and omega. So how much is v? V, it's omega times radius. So how much is omega sub 0? That's going to be v sub 0 divided by the radius. So if I introduce those things there, I'm going to have 1/2 mass v square sub 0 plus 1/2 times 2/5 m mass radius square times, that's inertia, times omega square sub 0, which is going to be sub 0 r square. And look what happened in here, that's mj, and that's just simply the height, which we just can leave it there. Okay, that's the question actually we're trying to solve. So we're gonna see over here, well, that this radius cancels, and what we find is that this is 1/2 mass v sub 0, 1/2 mass velocity initial square plus that's gonna be 1/5 of the mass, radius and radius cancels, square of velocity. How much is 1/2 plus 1/5? That's going to be 7/10 mass v sub 0 squared, and that's mass gh. The masses cancel, and so we're going to have that h, and I can write it somewhere, maybe let's write it here, that's kind of the solution. H is equal to what? H is going to be equal to 7/10 of v squared sub 0 divided by g. If we take v sub 0 to be 20, that's going to be 400. 400 divided by 100 is 4, times that's going to be 400 divided by 100, so that's 7 times 400. So how much is that? That's of course 28 meters. So that's the distance. That's the distance that the object will travel until it runs out of energy. If you had tried this problem without rotation, the height would have been different. Why? Because you would have been smaller. Why? Because you would not be considering that the object is coming with kinetic rotational energy, right? So it would just have come maybe all the way up to here. Because we are considering it, so if you take this to be 0, then what's the velocity, the height that you're going to find? You would find 400 divided by 2, 200 divided by 20, so 20 meters only. Because we're accounting by the fact that the energy is kinetic rotational energy, there's a more amount of motion, and because there's more amount of motion, the thing goes up there. If it was just without kinetic rotational energy, if the ball was just sliding, then this will be 0. And so the only energy we have will be this. If you solve for that, you're going to see that's 20 meters. So 28 meters because it rotates, 20 meters because it does not. Indeed, rotational kinetic energy is something that we need to account for. So let's say that we were the first physicists developing these ideas, we come up with the kinetic energy and we just drop the ball and see it doesn't reach all the way up to there. Hey, what's going on in here? There's a difference in height. Why is that? And then I have two options. I either say conservation of energy is fake, or I say there is another source of energy that needs to compensate for this, for the fact that the ball doesn't reach all the way up to there. Why doesn't? And I realized the motion is also happening rotational. I need to come up with a kinetic energy that is rotational. If you introduce that, then everything works nicely, and then you observe exactly that. So that's one of the things that Galileo was doing experiments. Whether you do the experiments rotating or not, you're going to have different heights, and the fact that there's going to be always friction is also going to perturbate your experiments. But if you account for everything anyways, conservation of energy still works. The change in energy needs to be 0 because there's no external forces, meaning there's no work. There's no net work coming from the outside. The ball can reach 28 meters. Now think again if you had to solve this problem instead of using conservation of energy from another standpoint, for instance from Newton mechanics and kinematics. This simplifies our process, and it's actually a nice method to get to a solution that makes sense again, because energy cannot vanish, cannot be created. Energy needs to be conserved if nothing comes from the outside of the system.